Okay, so I'm going to go through Astrophysics paper here, AQA paper 3 section B, so it's the optional paper and it's 2023, and Pedro here in classic pose, ready to help us understand the universe. So question 1, we have to draw a diagram to define the parsec. We're only getting 1 mark for this, for drawing a diagram. There we go. A parsec is a distance. So it's a big distance in space. It's equal to 3.26 light years. That is on your formula sheet. But what you need to do here is define how do we come up with this distance. So this distance is related to parallax, the parallax angle. I'm just going to do the define the parsec here. So let's assume we've got the sun here and we've got the earth here. And we've got something we're measuring the distance to. And we draw a triangle between these 3 things. Okay. Right. When this angle is 1 arc second, so the angle of parallax is 1 arc second, or 1 over 3,600 of a degree. At that point, we will get a right angled triangle with this being 1 AU. So the distance, an astronomical unit, the distance between the Earth. I'm going to label that just to make sure we get the mark, and the Sun. And it is the adjacent that is the parsec. So we're going to label this as 1 parsec. Now, in practical terms, this angle is so small that the length of the adjacent and the hypotenuse are so big compared to the length of the opposite, the 1 AU, that essentially for most purposes the difference between the adjacent and the hypotenuse is negligible. So in terms of difference is negligible. So in terms of the exam paper, it will allow you to have either of these sides labelled as a parsec, but by definition, technically, it's the distance from the sun to an object where the parallax angle is 1 over 3,600 of a degree. So there is your diagram. Please use a ruler when you're doing it. I haven't worked out how to kind of easily do rulers on this, but use a ruler. And you need to have the angle labelled either 1 arc second or 1 over 3,600 of a degree. You need 1 AU and you need the parsec labelled. Okay, another 1 marker, we've got to say the spectral class of Rigel. And you've just, quite simply, you just have to learn the table on spectral class in the specification. Here's the mnemonic we've used. So only bad astronomers forget generally known mnemonics. And then obviously we need to remember some information within that. So the temperature of O class is 25,000 to 50,000. And then B class is 11,000 to 25,000. And so Rigel is a B class star. Okay, so we've got Pedro trying to stretch his arms out between the solar system and Rigel. Is that to scale? Who knows? How big is Pedro? So we've got the apparent magnitude is 0.11. And from the table that we had previously, we have that the absolute magnitude, so our capital M, is minus 7.84. Now, I'm not going to go into the whole scale, but remember, apparent magnitude, how bright it appears to be from Earth, and the absolute magnitude, how bright would it appear if it were 10 parsecs away from us. Remember, the smaller, the brighter, and the more negative, the brighter. So Rigel has an apparent magnitude of 0.11. We need to calculate the distance between the two, and of course, we're going to use this equation here from our formula sheets. 5 log d over 10. Now remember that distance in this case is in parsecs. So that's in parsecs. and that is how we're being asked to leave our answer in parsecs. Okay, so firstly, if we bring the 5 down, so we get to here, and then we want to get rid of this log. So if we do 10 to the power of m over minus m over 5, that will give us d over 10. So I'm just going to do all that. I'm just going to pause and come back to this when I've written it out. Okay, so just made this a bit bigger because it was getting a bit small and messy. We are adding because obviously we've got the apparent magnitude minus the absolute magnitude, but the absolute magnitude is negative. So we're going to do that over 5 equals d over 10, and therefore brought the 10 up 10 times 10 to the power of 1.59 gives us the distance. And if we do that, oh, got a bad colour there. If we do that, got a bad pen there, hold on, apologies. Right, if we do that, the distance we get on our calculator reading in parsecs is 389. So let's have a look at what values we're given. So we're going to leave that as 390, aren't we? So our final answer is 390 parsecs. Okay, there's my slightly ropey HR diagram, but the Hertzsprung-Russell diagram. We have absolute magnitude. Remember, as the number gets smaller and then negative, the magnitude is increasing. It's getting brighter. We've got spectral class down the bottom, and we have supergiants, giants, main sequence, and white dwarfs. And we have to draw a line to show the evolution of the sun from formation to a white dwarf. Now, what we need to do is start off in this area here. Okay, and the mark scheme shades an area like this for where our sun will start as a protostar. So it's going to be very cool to start with. Remember, our spectral class is related to the surface temperature, and so down here we have the hottest stars, and here we have the coolest stars, and when a star's just starting to form, it's going to be very much a cold star. We're then going to move, if we're a sun like the star, we're coming from over here, and we're going to move into main sequence. And where are we going to get in main sequence? The sun is a class G, and it's going to be coming into around this area here where the magnitude, the absolute magnitude, is about 5 and the class is G. So here's our sun as a main sequence star. Then it's going to become a red giant. So it's going to head back this way because it's going to get cooler and be in the giant stage before it, I'm not going to do white because it might not show up very well, before it then heads its way as it goes to the next stage of its life as a white dwarf star, where it will have a very high surface temperature. It's white after all, but will be giving out a lot less energy, just that core left over. So a bit messy there, but hopefully you can get the idea. We're moving from protostar in this region to main sequence as a sort of absolute magnitude 5 class G star, up to a giant star, and down to white dwarf. Okay, outline the circumstances during which a gamma ray burst will be emitted by Rigel. I'm just going to pop up the specification point that you need to know for this. Gamma ray bursts due to the collapse of supergiant stars to form neutron stars or black holes. So do not confuse gamma ray bursts with quasars. Quasars are different things. Gamma ray bursts are one of the most powerful explosions, things that happen in our universe, but they last for a very, very short amount of time. Now, what you may be thinking is you more naturally think of a supernova when you think of a supergiant star collapsing. That is, of course, what can happen. That tends to go on for a number of weeks, up to months. A gamma ray burst is a very short and even more powerful event that happens as part of that collapse, and kind of during a supernova, but we consider it as a kind of separate event, a very short event, tending to be seconds. Hours would be a long gamma ray burst. So there are 2 marks here, and it's about saying that a supergiant collapses. So the first mark is saying that it occurs when a supergiant collapses, and the second mark is for saying when it forms a neutron star, or, and or is in bold in the mark scheme, or a black hole. So basically, if you learn that specification point, you get these 2 marks. So mark 1, the collapse of a supergiant. A gamma ray burst happens when there is a collapse of a supergiant, when it is forming a neutron star or a black hole. The mark scheme says ignore references to supernova. That means you don't lose marks if you included supernova in your answer, but it's also not credit-worthy if you don't get any credit for saying supernova. Okay, I hope that was useful. That's question 1. Let me know if you want me to keep going. Take care.